Hello guys, this is a do-over retake of the lesson I taught on Monday, and I'm going to start right from the beginning. And I'll grab a pen, and this is where I would start with a class doing an intervention session, and I'd get them to write P1 motion on the board, or P2, wherever we're up to. And then I would go around the room and we'll see what we could try and remember from P1 motion. So if you've got your notes in front of you, you'll find this quite easy to recall. And what we're really trying to do is make sure no one's forgotten any of the key points. So one of the two big things I would start with is talking about vectors and scalars. Okay, and I'd straight away be looking for an example so we can tease out the really important things. So a good example of this would be if I said you were going 30 kilometers per hour west, or if I just said you were going 30 kilometers per hour. Now they both have the same thing in common. They both have magnitude. Okay, and that's the 30 kilometers an hour bit. So both vectors and scalars have magnitude, but only one of them has direction, and our vector has direction. Okay, so if I said I was going 30 kilometers per hour west, it would be a vector. If I just said we're going 30 kilometers per hour, it would then be a scalar, because they both have a size, but a scalar doesn't have a direction. Okay, so a classic example of this that you'll come across in physics: velocity is a vector and speed is a scalar. You'll never know or be able to remember how I can remember which one's which. Let me see if I can give you a helping hand there. Hopefully that's pretty obvious now. Okay, so that's vectors and scalars. Another big thing that comes up in tests, and people forget that a big part of physics is being able to interpret graphs. So we look at distance versus time graphs, and we might draw one. And in fact, in class on Monday, both of the first two classes, we did just that. And we put distance on the y-axis and time on the x-axis, and I drew this, something similar to this. Ooh. Something like that anyhow. And I started labeling things up: A, B, C and D, and there's a couple of questions that come out of this. Firstly, what's happening at point B? Well, at the start of B to the end of B, the distance hasn't changed. We're stopped, we haven't moved, so B stopped. Okay, that's a nice easy win, easy mark there. The other big question that will come out is, what's the difference between A and C? So the difference question mark between A and C. Well, we know if B stopped, A and C are moving, the distance is changing, so they must be moving. But very quickly people will be able to say, well, hang on, C is steeper, it's meant to be straight, C is straighter than A, steeper even than A. So if C is steeper, it means we're traveling faster. Not that A, we know how fast this is, it doesn't really matter, we just know that C is faster. And the key word we're looking for here, guys, and I'm just going to write it really big up here: gradient. The gradient tells us speed. It doesn't tell us necessarily, unless we know some of these figures. We haven't put any numbers on this graph at all, but if we put numbers on, we'd be able to say exactly how fast it's going. And the very last question is, how far have you traveled at point D? And believe it or not, all you need to do is go across the graph to the distance and read off that point there, and they'll be looking for some accuracy there. Can you draw a straight line with a ruler on a graph? The answer is yes, but please use a ruler and draw a straight line on a graph. Thin straight line as well. Don't use a big fat pencil, you'll end up getting an answer that could be plus or minus 2 or 3, where they're giving you plus or minus 1. Okay, so that's distance versus time. And the other type of graph that comes along quite often is velocity versus time graph. And again, let's draw one over here, and we'll put velocity on the y-axis and time on the x-axis. And the big thing with the velocity time graph is interpreting the overall picture, what's happened over the whole course. So right at the start of this question, when we're here, so we start right in the origin, our velocity is 0, time 0, velocity 0, and our velocity is increasing. So let's put A, B, C. So at A, velocity is increasing, which means we have positive acceleration. Now, because it is accelerating at a positive rate, a constant rate, because it's a straight line, which means we could use our constant acceleration equations, but let's not get on too far ahead of ourselves. At B, now this is a big misconception. At B, because it's flat, and we talked about up here in a distance versus time graph that flat means stopped, but this is a velocity versus time graph. So B means speed, not stopped, constant. So use these keywords. So we've got gradient up here, and gradient's just as important down here as well, but speed is constant. And in C, we're not stopped, we are slowing down, we're de-accelerating, or we have a negative acceleration. There's a few interpretations of how to say that, but effectively you're slowing down, your velocity is reducing, until eventually you get to a velocity of 0. And the number one question that comes out with the graphs like this is, how far has this person traveled? Well, the great thing about velocity time graph is the distance underneath the line, and I'll write distance under line equals distance area sorry, underline equals distance traveled. See, it doesn't matter how many times you do this, you still make mistakes. So this area in here is the total distance traveled. Well, it's actually made up of a triangle, a rectangle-ish, and another triangle. So if you can find the area of a triangle, so just to remind you, that's half times base times height, plus the square, which is just base times height, plus another triangle on the end. You can, if they're the same size of course, terrible maths if they're different, you can add up and find out the total distance and do it mathematically, or you can sit there and counting squares. Personally, I'd like to do it mathematically and do it quickly and get it accurate. But that is main difference there, guys, between a distance versus time and a velocity versus time. Now, you'll probably notice that I'm spreading around my information into chunks, areas where I know that key questions come out time to time. I wouldn't suggest yours looks this messy, but make sure you don't add lots of writing. Try and keep it more graphical, so that prompts your brain to remember what's going to be asked. Right, let's come across the left-hand side. Let's write these lovely letters here. And I don't get them perfectly straight in, it doesn't matter. It doesn't have to look perfect. This is about recall. And these are the suvat equations. So, displacement. Oop, I can spell. Our initial, this is far more fun when I get you guys to try and remember them. Initial velocity, so remember it's a velocity, so it has a direction. A final velocity, the constant acceleration equations, and that's really important. Let's write that word up there again, constant acceleration equations. Now, if your acceleration isn't constant, you cannot use these equations. So if they show you a graph, for an example, where the velocity changing is not in a straight line, it's in a curve, you can't use these. You might be able to take a snapshot, a single point somewhere on that graph, and draw a tangent to the curve, different issue, but otherwise you can't use the constant acceleration equations. But that A, if it's not obvious by now, acceleration, and T is for time. Let's quickly go through the units. Displacement always in meters. They might give you something in kilometers or centimeters or millimeters. You need to change it to meters. Let me just make that a bit tidier. Our velocities in meters per second, both of them. Our acceleration, meters per second. Sometimes that's written, depending who's teaching you, like so. That doesn't matter, they mean exactly the same thing. Okay, it's just in A level we switch over to meters per second to the -2 indice, but it's just because it's faster to the right. They do mean the same thing. Time, always in seconds. Biggest trap they'll give you here is they'll tell you something takes 3 minutes to come to a stop. If you put the number 3 into your equation, it'll assume you mean 3 seconds, and you'll get a very strange answer. You need to convert things to seconds. Okay, so what are our constant acceleration equations? Right, here's the first one. This is the non-negotiable. You must know this equation. And it does come up written as sometimes different in the textbook. It basically says a final velocity minus the initial velocity divided by a time will give you an acceleration. All this is a rearrangement of each other. Okay, I do generally find most students find this one on the left easier to remember, but if you're very good at rearranging equations, it doesn't matter which one you remember because you'll get to the same thing. The second one is v squared equals u squared plus 2as. Now I'm going to hesitate for 2 seconds because in Edexcel physics, the science curriculum that we use, they don't use the letter S, they use the letter X. So they cross the X out and put X instead. It makes no difference, it's just a letter for algebra, except suvat doesn't really work and everybody else uses suvat. And if you want a real chuckle, if you're using Edexcel and you go on to A level, we go back to, you guessed it, suvat. So there's not much consistency there, but all you need to know at this stage, guys, is you might see it with an X rather than S. Makes no difference, you're still substituting that in, and I'll put X down here, put that in brackets next to the S just so there's no confusion. You know it's called suvat, but you'll see the X in the equation instead of an S. Alright, the third suvat equation isn't actually in your spec, but we sometimes use it because it's, you know, it's a good learning environment. It's actually a really good one to do practicals with, and it's ut time plus half of at squared. You'll notice that time's in there twice. It's a quadratic equation. We spend loads of time on this in A level. Whilst you don't need to know how it's formed in GCSE, it is straightforward. Drop in numbers and you'll get a distance something travels in a given time. Very handy for things that are falling, like a skydiver jumping out of a plane. But you'd be given this equation and you'll almost be certainly directed to it in the question. So it's at this stage, these two are practice. You don't have to memorize them, they're just practice. This one, on the other hand, you need to memorize. Okay, you have to practice it so many times you don't have to even think about memorizing it. It's glued to the back of your brain. Right, so it's only fair that we do a suvat question to finish this off. So, and I'll demonstrate one, and I'm going to use the side of my page here and make a little cliff. Okay, and these are little waves at the bottom of the cliff, and we're going to have a diver who is an expert cliff diver, because we don't do this without expertise or knowledge or skill. And our diver is going to jump off into the water, and let's give this diver, let's make it a very precarious 43 meters. I'm just making these numbers up, and I would like to know the question mark. How fast is the diver going when they hit the water? Now, you probably, if you remember back to study year 9, you probably discovered it doesn't actually matter the mass of the person, because in all of these equations there is no mass. The mass is irrelevant because all objects are affected by gravity at the same rate. So we can, once we work out what we have, so what I would recommend to most students is, if you're not sure which equation to use straight away, write down the letters S, U, V, A, T. Let's see what we got. S, we got 43. Good. U, now this is in third. We haven't been told his initial velocity is 0, but he's standing on the top of the cliff. Then he jumps off. So we're having to work out from the type of question that his initial velocity is 0, and that's quite handy for us. His final velocity, well, that's our unknown question mark, And the reason it's going to accelerate is due to gravity. And the number we always use is 10. Please put that somewhere really big. Gravity, use 10 meters per second for acceleration. Okay, really important. At GCSE, at Edexcel, we use 10 all the time, even though we know it's not 10, but it's close. Time, we don't know time. It's not given to us. We are not working it out, so we'll put a cross there. So straight away we know we need an equation with S, U, V, and A, N. Straight away, well, T is in the first one, T is in the third one, it means it's the second one. So let's write down the equation that we're going to use. So straight away I've got a nice methodology going on here that I use every single time, because that's good practice, even when I'm solving in real world questions, because if I make a mistake, it's easy to follow. So I want to know what velocity is, so I need to get v on its own. I need to make v the subject. So I've got v squared at the moment, so I need to get v to a singular, so I'm going to square root it. So if I square root v squared, they cancel each other out. I end up with v. But if I square root one side, I have to square root the whole, that's important, other side. Okay, so now I end up with v equals square root of u squared plus 2as. So now I can just substitute my numbers. I've already earned most of the marks in this question because I've pulled the numbers out of the question. I've taken the right equation, I've rearranged the equation. All I have to do now is solve. So if this was out of 4 marks, I'm already 3 out of 4. So square root of 0 plus 2 times 10 times 43. So 430, so we've got 860, square root of 860. I'm not even going to pretend I can do that in my head. Let's get the calculator out and quickly drop that in. So I've simplified it as much as I possibly can before I get to this stage. Producing errors. So I get an answer of, now I've got to find my pen again, 29, let's just go to 2 significant figures, 29 meters per second. Don't forget units. Okay, so that's a classic example of a suvat question. So if I saw this piece of paper in front of you when I've asked you to do a P1 revision mat or a knowledge organizer of your own, I would be nothing other than impressed. Okay, what I'd be even more impressed is if you took this and cleaned it right up and simplified it right down. Now there's not a huge amount of excess information on there. It's pretty much all the important things that would cover most of P1 motion. There is a lot of overlap with P2, so don't try and squeeze all the P2 stuff on this one as well. Start a new one for P1. This would get you going, guys. I will produce more of these as we go when I do live lessons with students in school. And I think Mrs. Porter for the year 9s is sending these out when they're appropriate, so only if it's covered in your end of year exam. I don't want to give you stuff that you haven't been taught yet. Otherwise, year 10, if there's anything I put on this board that confuses you, you're not sure about, I've made a mistake, anything at all, please email me. I am more than happy to email you back and either steer you in the right direction or admit that I've made a mistake, because that sometimes does happen. But so far I think we're looking pretty safe on this one. It's just the one question on the board. But if you've got any other questions you've been trying and you're stuck, send those through as well. I will try and use them in the recordings as I make them. Otherwise, take care, look after yourselves, and for those I see in class, I'll see you next week.